So remember, we were looking at the Fitsunagumo equation, which was like this, where this was a cubic. And so we had this. One thing I should have mentioned is that since V is related to potential, it can be negative. So it's negative there. And then we had this threshold phenomenon. Small perturbation goes back to the steady state. Large perturbation does go back to the steady state eventually, but after a long excursion. So now what happens if we make IA not equal to naught? So the applied current is not equal to naught. So remember, the V null line is W equals IA plus FV. One thing I should say, and leave it to you to do all the different cases. Remember, we've got it like this. It could actually be like this, which would give 3 steady states. And then you could see what would happen when you make the perturbation. This would go up, and then it would stay at that steady state. Okay? So maybe just put that in. If W, if it was like this, say. Then again, then what would happen, you make small perturbation, you go back. You make a large perturbation, you go up, but then you would stick there. So that's called bistable state, bistability, or a switch, where you can go from low to high, okay? And if you add IA in, all that does is lift this up. Lifts the parabola up. So you could imagine having the case where so if we draw this one in first. And then this one, oops. Say, look like this. And now what you will see will happen. Now you've only got one steady state, which is this one. And so, for example, if you were to start here, maybe a little perturbation from here, you would shoot across to there, hit vertically, go along like that, and go to there. Okay? So what you can see is that if this blue null line crosses this branch, and this branch only, then you've got one steady state and it's stable. If it crosses this branch and that branch only, then you've only got one steady state and it's stable. If it crosses all the branches, then you've got 2 steady states, which are stable, and an unstable steady state. So the last case for us to do is what happens if it only crosses the middle branch. Okay? And so get it crossing middle branch. Right. And now we've got one steady state. So let's do perturbation. Remember, below this line, the V dot is positive, and W dot is positive, so it will grow, and it'll grow very fast. It'll cross this vertically, it'll move along this null line, and then it will have to go off because it can't go down because the W dot is still positive, so it can't go down. So it must leave that, crosses it, goes along to here, then comes down here, because below here V dot is positive, and then it comes to here, and then it wants to go along here, but that would mean W increasing. But we're above here, so W is still decreasing. So it has to go across like that, goes like that, up like that, and then on like that. So what you get is a periodic solution. So we plot as a function of time what's going to happen, and we started off here, some value V. So V very rapidly increased, then slowly started to decrease, then rapidly decreased, and then slowly started to increase, and then rapidly increased, and then started doing like that, okay? Meanwhile, W maybe started here, stayed virtually constant during this one, then increased slowly, then stayed virtually constant in this one, and then decreased slowly, and then stayed, then decreased slowly, and then stayed virtually constant in that one. Then increased, then decreased, okay? And so we call this periodic firing. Now, one thing that I should mention is that this model and models like this have been used to model the heart, where in the heart the electrical current flows through the heart, it stimulates calcium, and that affects the mechanics of the system, and the heart closes and then opens and closes and opens, so it beats. And one of the very first mathematical models of that was by Dennis Noble, who's here in Oxford. And I should say that now there are whole heart models, where people model all of the heart and look at these waves. And drugs for the heart, they tend to affect the ion channels. So the question is, if you affect the ion channels, how does that affect this? Okay. And mathematical modeling is now used a lot, for example, by the Federal Drug Administration in terms of seeing whether some drugs should go to eventually go to use. It's a mixture of modeling and experiment. And one thing to point out is, of course, the experiments are very much very much more expensive than the mathematical modeling. So it gives a sense of mathematical modeling helping to reduce the cost of a drug. Okay? Because in a lot of cases, when you're paying for a drug, you're actually not paying for that drug. I mean now legitimate drugs, okay? You're paying that company back for all the drugs that didn't work, that went through a lot of trials, they spent a huge amount of money, and then it failed. They've got to recoup that money, and they recoup that money when you have a drug that works, okay? So now we're going to leave that sort of physiology and medicine and go on to the final chapter, which is infectious disease modeling. And this is in Ruth's notes. Chapter 5. Okay. And so here we're going to look at the simple model, which actually is the classical model. And it's called the SIR model. Okay, so once again, we're going to be considering ODEs, so we're going to assume that there's not a lot of movement. Okay? I mean, that's one thing I should mention, is here, for instance, here, and a lot of the other things we've been looking at, we've talked about what would happen if there's no movement. But all of these things move. So for instance, here you get propagation of waves. That means you need to have a PDE, you need to take X into account. And later courses will look at that in later years. When you've got PDEs, how do these work? How do you get these oscillations? How do you get traveling waves, etc., etc.? But we're focusing on the case where we ignore movement. So what we have here is S are the susceptibles. These are people who can catch the disease. And then I, we're going to call infectives. And here we're going to make an assumption that these individuals have the disease, and can spread it. So they're infected and infectious. Okay, because as you know, with most diseases, you get infected by the disease and there's a delay before you can transmit it. Okay, so you could write down a delay differential equation here, but we're not going to do that. We're going to assume that as soon as you get the disease, you can pass it on. Then R is removed. And that means individuals removed from the spread of disease. And that means either they've become immune or they've died. Okay? And so the classical model of this, again, making all the assumptions, time is continuous, there's no immigration, no emigration, and this is the Kermack McKendrick model. developed in 1927. And what they said is assume that the time scale of the disease is short, so that there is no birth nor natural death. And then, if you like, we can actually use the law of mass action here. We can say that S plus I gives you I plus I, okay? Because that susceptible turns into an infected. And then we have infected turns into removed. Okay, so the usual thing, writing S to be that. Well, now we'll abuse notation, okay? So we'll just write S, big S, etc. So abuse notation. So we're going to get ds by dt equals, so S is lost here, minus RSI. In other words, susceptible meets an infected, and with this rate, they become infected. These infecteds go to here, and then the infecteds become removed. So make sure I use the same A. So A, then dr by dt is AI. So RA positive constants. And initial conditions, you have some susceptibles, you have some infecteds, and you have no removed. Okay? So you got a system of 3 ODEs. And notice that if we were to have natural birth and death, then we'd have like a plus some birth term there, maybe logistic death, maybe minus D times S, and minus D times I, etc. So note, first thing to note is that this equation decouples from these two. So we just need to solve these two equations. So we're back to solving 2 ODEs and phase plane analysis, steady state analysis. Okay? So R is decoupled. Second thing to note is if we add up all the equations, S plus I plus R is 0, which means that S plus I plus R is a constant, which is the total population. And now that's what we would expect. If all that's happening here is you're getting conversion from S to I and then to R, then there should be conservation. That's the way to check you haven't missed something out. I should also add here another assumption within this model is that when you've got the disease and you get to remove class, you are immune. Okay? But you could have a system where you go back to being susceptible. And that's called an SIS model. Now, there are other diseases, like, for example, Ebola, where people can catch the disease from the funeral ceremony. So in that case, you would have the big R up here as well. Okay? So depending on the disease you're modeling and the detail you want to go into, you would have different versions of this. Okay? So this is just one version of disease model. Okay? So what's this constant? Well, that constant will be what was the total at the beginning, which is S0 plus I0. Okay? And so now you see, if you solve the top two ODEs for S and I, and then you just substitute that into the next, into that linear equation, and what you end up getting will be R. Okay? So here we're not going to non-dimensionalize because we want to keep little r and a in, because they've got sort of important interpretation. So R is the rate of spread of disease per susceptible. Okay, because so R will have units 1 over t times person. So in other words, it is the rate of spread of disease per you could put it in as per contact between S and I, okay? Or per contact. You could either have that, or you could say it's the spread of disease. There's a number of ways you could write it. Actually, maybe instead of doing that, you could either write per contact between S and I. Maybe write it as that. Okay. Right. So now if we draw the phase plane, oh, sorry, I've got that the wrong way around. So what we have is oh, sorry, I had it right the first time. Sorry about that. This should be I, that should be S. So ds by dt equals 0. Well, both of these. And inside here, S dot is negative. And then we're going to have the I by dt equals 0. That gives us I equals 0, or I equals R over A times S. Okay. Sorry, that's wrong. That gives you S equals R over A. Got that totally wrong, right? Because you can cancel the I, and then S is A over R. Make sure I've got that right. Yeah, that seems to be right. Okay, so I equals 0 is the this line, I equals 0. And then S equals A over R. Let's call this rho. That's going to be this line. I dot equals 0. So let's see if S is very small, the I by dt will be negative. If S is very large, I dot will be positive. Okay. So now the question is, what's our initial condition? So initially, since R is 0, S plus I equals N, which means that the initial conditions must lie on this line. So suppose this line looks like this. And then suppose we start here. Then I dot is positive, S dot is negative, so we'll increase. And then we cross here horizontally. Now I dot is negative, so we decrease. Notice that in this case, we've actually got a continuum of steady states. So when this comes down, so in the past, we've had the trajectory goes to a steady state, for example, or circulates or something. Now what we have is it goes to some value down there. Okay. On the other hand, if we started here, we'd go like this. Now we could have another setup with null lines, same thing. Well, maybe put that over here. And then this other one. And then you'd have this one down like that. And now what happens? No matter where you start, you go down like that. Okay? So two different cases. So crucially, this case here is called an epidemic because I increased at the beginning. So we call this epidemic. And we can see that happened because this rho was this value, but here there's no epidemic because rho is over there. And we can get that quite easily, again, from looking at di by dt. di by dt equals I into, let's write it like this. Make sure we got that right. So so I comes out, and if we take the R out, we have to divide by R. Is that okay? And so we see that di by dt at t equals 0 is R I naught into S naught minus rho. Therefore, S naught bigger than rho implies growth, and therefore epidemic. R S0 less than rho implies I decreases. Okay? i.e., if S naught over rho is bigger than 1, that implies epidemic. Okay? i.e., remember what rho is. Rho is A over R, so that's R times 1 over A. Okay? Now let's look at that term. What is that? That is, if you go back up and look at the equation, ds by dt is minus RSI. So at the beginning, we've got S as S naught. And if we had one infective person, this would be the number of new infectives, we've called them, created by one infective in an otherwise wholly susceptible population. Okay, so in other words, if you've got one infected and everybody else is susceptible, then RS naught is the number of new infectives created by one infective, and that's per unit time, because it's ds by dt per unit time. Now, A equals the rate of movement from I to R. If you look up there, AI. So that means 1 over A is the time spent being infected. Because if A is the rate at which you move, then 1 over A is the time spent. And so now you see, if this is the rate of new infecteds created per unit time, you multiply that by the time you spend being infected, this whole term gives you the number of new infecteds one infective created. Okay? So, therefore, RS naught over A is the number of new infecteds created by one infective in population size with S0 susceptibles. And now this makes sense, because if the number of new infectives that one person creates is bigger than 1, the disease will spread. If it's less than 1, it means you're producing something that's less than what you've got, then the disease will die out. Does that make sense? Okay. And this number is called R0, R naught. And that's the R value that we heard so much about during the pandemic. So what this is telling us is we must reduce R naught. We must make R naught less than 1. How can we do that? We can reduce R, which is a measure of how the disease can spread. So how could we do that? Well, we do that by being far away from each other, having distance. We can make R naught smaller by increasing A. A means the rate of removal. Now with COVID, there were 3 ways you could remove yourself. Well, you couldn't remove yourself from immunity before we had the vaccine, and it wasn't known whether we could be immune. Unfortunately, we could remove by mortality, but a 3rd way that you could remove yourself from the disease is stay at home, isolate. Means you're away from all the population. And then S naught, we could decrease that. That's the number of susceptibles. And again, we could do that. Well, now we've got vaccination. We can do that by vaccination. In the days when we didn't have vaccination, we couldn't change S naught. But what we could do was remove ourselves from everything, okay? And so now what's happening is we no longer remove ourselves from everything, but we have vaccinations, and that decreases S naught. So the last thing I want to do in here is, in all these drawings I've done, why did I come down like this? Why did I not go like this? See, in all of these things, the disease transmission dies out because I goes to 0. But what about this? If it went like that, the disease would die out because S went to 0. So is there a curve that looks like this? So let's look at, let's go over here, ds by dt equals minus r si. dr by dt equals ai. That implies ds by dr equals r over a, which is 1 over rho, and s, and minus. And that gives us that S is S naught e to the minus r over rho. Let me just check I got that right. Okay. What is R? R is n minus I minus S, and R is bounded by n, big N, because I and S cannot go negative. Let's just check that I and S cannot go negative. If S went negative. It started off positive, it went negative. That means it's decreasing, which means that s equals 0, ds by dt is negative. When s equals 0, ds by dt is naught. So it can't decrease. What about here? Could I become negative? Same argument. If it was to go negative, starts off positive, at some point it has to pass through 0, going downwards. So di by dt has to be 0 at that point, has to be negative at that point. When I is 0, di by dt is 0. It's not negative. So I and s are bigger than or equal to naught. And that's a good job, because our model would be pretty useless if you could have negative populations. Now, a lot of people say, when they're doing this, they say, oh, s and I are populations, and therefore they can't be negative, and therefore this is positive. Well, that's wrong, because how do you know that your model stops I and s from becoming negative? Maybe you've got a very bad model. Okay, so here's my model for infecteds. Infecteds equals -6. That's my model. Oh, infecteds, that's a population. That has to be greater than or equal to naught. So -6 is greater than or equal to naught. Okay? Right? It's not, by the way. Okay, so what that means is that s is greater than s naught e to the minus n over rho. Okay, because r, the maximum r can be is n, and therefore the minimum this can be is e to the minus n over rho. So that's that, and that's greater than or greater than 0. So it's s is strictly greater than 0. And that's why it doesn't go through here to here. Okay? And note, as t goes to infinity, s of infinity will equal s naught e to the minus r over rho. Well, now we've figured out that the disease dies out when I goes to 0. So when I goes to 0, big R is n minus s of infinity. So what we've got here is a transcendental equation that allows you to find how many susceptibles are left. And of course, I forgot to put rho in there. Okay? So you can figure out how many susceptibles are going to be left by solving this transcendental equation. And we can't solve that explicitly. Okay? We can only solve that graphically or numerically. Okay? So what we could do, and we'll not because it's beyond this course, is we could say, well, okay, we could either have a delay in infecteds. So we could go that there's a delay between becoming infected and spreading the disease. We could make life a bit simpler by still having ODEs, by having you're susceptible, then you're exposed, which means you've got the disease but you don't spread it, and then you're infectious, and then you're removed. So you've got SEIR model. And then maybe sometimes you can be immune and sometimes you're susceptible. So you've got S, E, I, and then you could go to R or you could go to S. And then we could have, since this doesn't have space in it, we could have communities. We could have networks. Okay, so people living in one place model that as an SIR model, but then they move into workplace where there's another group of people, another SIR model there, and then you've got movement across there. Okay, so you'd have here S1, I1, R1, here S2, I2, R2, and then movement across. And you can imagine having a network, a very, very complicated network. And then where you can move all around. You can make this very, very complicated. And as you all know, this type of modeling was used in during the pandemic, and some of the people in Oxford, I mean, okay, and not only was that vaccine, AstraZeneca vaccine, invented by people in Oxford, but a lot of the modeling and stuff like that that was done, and a lot of the checking that went into the models was done by people in Oxford. And in fact, one of the people that was heavily involved in SAGE is somebody called Robin Thompson, whom we've just hired last year. Well, last calendar year, this academic year. Okay, so where do we go next? Well, in terms practicality, in terms of courses, there's further mathematical biology in third year, and what that does is it takes space into account. What happens now if you allow everybody to move, allow your chemicals to diffuse, etc., etc. So you get what are called reaction diffusion equations. So the reaction part will be all these bits that we've done in the course. How do things interact? And the diffusion part will be how do they move? And then in the fourth year, there's stochastic course. Now, one thing that we haven't embarked on here or mentioned, when you get down to here and I gets very, very small, then random effects can be very important. Because here, when we write down a density, we're assuming that there are a sufficient large population that we can talk about a density, and that a little blip is not going to really affect things, okay? But when you get down to very, very low levels, maybe 2 or 3, then you have to take stochastic effects into account. Some random event might happen, okay? You know, if you are a deer and there's just 1 or 2 deer and they cross the road and just happen to get hit by a car, then the deer population goes to 0. A random effect happened. I say that because I did see a dead deer last week as I was cycling into work. But here, a random effect just doesn't account for random effect. So you need to have stochastic processes in. And then in all of this, well, when we talked about biology and chemical, we talked about chemical reactions, enzyme substrate kinetics, we talked about ions moving back and forth, etc., etc. We didn't say anything about mechanics. Okay? How does the heart beat? For example, how do cells move and interact with each other? and that's called mechanobiology, and that's in the 4th year. And then going deeper into things like the Fitch-Ngurumo equation in physiology, looking at things like blood flow, etc., that's in the 4th year physiology. Now, we have focused here on the mathematics of things. You can imagine as these become more complicated, you have to solve them numerically. So there's a lot of numerical analysis and computation that goes into mathematical biology. Not done on the mathematical biology courses, but if you're a professional mathematical biologist, you have to do this. Moreover, if you want to compare these to data, you need to know something about statistics. And also, if you've got these networks of cells interacting, nodes interacting, you need to know graph theory, network theory, and topology. Okay? So it's very difficult for one person to know network theory, graph theory, topology, statistics, numerical computation, stochastic analysis, ODEs, PDEs, mechanics, and whatever else there is. So this is why mathematical biology is now really what's called a team science. It's one place that brings so many areas of mathematics together in a way that no other subject in mathematics does. So if you're a pure mathematician and you want to be a mathematical biologist, you can. You're really applied, you can. Statistician, you can. Numerical analyst, you can. Stochastic analysis, you can. Because biology has such a range of activity that it really is, and so many opportunities in there. And there's a saying, unfortunately I can't remember the name of the person, at the beginning of the century, he said that mathematics is biology's next microscope, biology is mathematics' next physics. In other words, how the microscope transformed biology, this is how mathematics will transform biology, and how physics advanced mathematics and meant you had to come up with new mathematics. Biology means we have to come up with new mathematics. Okay? So that is an absolutely blatant advertisement for mathematical biology to encourage you all to take mathematical biology courses later on. And the last thing I want to say is that thank you very much for being you coping with the fact that we had to rearrange to have this lecture this morning. Sorry that there was a bit of a mix-up in the scheduling, so thanks for being flexible. And good luck with your exams next term, and hopefully we'll see some of you later on. So take care, everyone.